Hi, SpeedCode here. Welcome to my fully fledged speed coding video, and the first one will be about a huge overhaul of the tree determination in the plugin TreeAssist. As for the many things lately, this came to light through a report on the SpeedCode page. Someone sent me a timings report, which, to be fair, wasn't really alarming to begin with. My plugin spent under a second per tree. However, the reporting user felt like this was an issue, so I asked them to double check that there actually is server lag, which I really did not see. However, I had some time on my hands and I did check into the block determination because I remember that I did not look into the algorithm for ages. I started looking into how trees were calculated, starting with the vanilla tree, which basically is the oak tree, but also supports the other 1.7 trees. The calculate method takes the top and bottom logs, which are calculated beforehand, the same way for each tree type. From there, each subtype calculates the trees, depending on several factors that vary from type to type. So remembering how many blocks I used to check in the beginning, per block of log found, I added some debug to see how many blocks I actually checked for whether they need to be broken later. So I added a little counter that would be incremented when checking a block and printed out later. I prepared a testing world full of all tree types and started with the oak trees because I assumed, because of their theoretically possible complexity, they would have the biggest impact on improvement. Testing this instantly showed two flaws at the same time. For some reason, the block size calculation got executed twice here, and we thus see the output twice. 1411 blocks for a single tree of roughly 30 to 40 blocks? This sounds insane, right? That's what I thought. And yeah, look at how slowly the tree is being processed. There's certainly room for improvement there. Given that the block list being processed with a speed of like 20 blocks per second, this visual speed is alarming. Checking smaller trees really did not look much better. This tree right here has 6 log blocks, but 126 blocks are being checked for whether they could or should be broken. So the first thing to do is to find out where the calculate method is being called. ID is find usages, shows that we call this method a total of 3 times. To find out which are called, I enhanced the debug with the numbers 1 through 3. Hitting a tree showed that 2 and 3 were triggered. That's at least better than having 2 run twice, but why is there a second calculation in the first place? I did not investigate this further, but I deactivated this part of the code for now, as the total blocks list was never filled at all, so this was always executed. It might interfere with the cleanup runner, but I will fix this using the remove blocks list later, instead of creating a second total blocks list in the first place. This is simply doubling the calculation for a reason I just do not understand right now. So for now, I went with literally cutting down the calculation time to 50% by removing the second calculation, which always got the exact same result as the first one anyways, so why do it? I removed the debugs and started committing the changes I did, so the reporting user got at least 50% of a cut down of the initial determination. When I looked at those, I noticed that I did some changes before starting today. I obviously noted my debug counting, the second check I commented out, but in the vanilla tree class, I started to found some boolean check, which basically verifies that the tree either has a full set of 4 bottom blocks, or the bottom array is null. The check whether bottoms is null is used in many places to determine whether we are dealing with a thin or a thick tree. So again, I committed this and skipped the oak tree for now because it is the most complex tree. There are easier things to tackle. Birch and spruce. This time I used the internal debugging function, which prints out every single block that it does check for addition to the block list to be broken. I activated debug, broke a spruce tree, a birch tree, and had a look at the debug output. As you can see, without even counting, these lines are way too many, compared to around about 8 to 10 blocks you would expect. Sadly, the window doesn't show the current and total lines, but I estimate them to be 44 lines per page, and there are about 10 pages, so 5 pages per tree means 200 blocks per tree, which is way too much. I checked an online wiki for more information about how trees work, or specifically what their structure is. Quickly I learned that only giant oak trees, dark oak trees, and giant jungle trees do grow branches. The rest does not. I first decided to create a new derived class called a branchless tree, copy the vanilla tree code over, and then decided against the name of branchless, because spruce and birch do have a big difference. Birch can be only thin, spruce can be thick, so we need two separate slimmed classes. I started implementing the new class as a spruce definition class, so I could include the thick tree implementation and only remove the oak all around check stuff. Basically, mostly edited out is me specifying the implementation by removing the non-spruce information that I checked in the vanilla tree before. I first checked with activated debug that the new algorithm still works on thick and thin spruce trees, which it did. Browsing through the debug, I found that for like a 200 block tree, including leaves, it would check a total of 1,700 blocks. This was pre-optimization, obviously. Another debug revealed that a tree of size 39, including leaves, did a check of a total of 250 blocks in the process. To tackle this, I split the block calculation method depending on whether it is a thick or thin tree. For the thick trees, I added a new discovery method, which basically takes the current trunk into account and its alignment relative to the trunk center. So the trunk in the smallest x and smallest z position should be the northwest chunk, and it would only need to check north, northwest, and west for logs. So for spruce, it would even only need to check for leaves, but the check block method does the same thing anyways. If it is a leaf, it exits and does not continue in the direction. So what I did is calculate the xz minimum trunk block and create a new method that takes north and west into account. Similar to the other calculation function, this method takes the bottom block to start with, the top block to end with, and the addition is two block faces that will check for logs or leaves. So cutting down the fat on the check block function, which basically decides on how many and which blocks are checked next, I could remove a check that was only necessary for oak and jungle trees. These trees can have branches intersecting with other trees or even other tree types, so you should still keep testing the environment for other fitting blocks. For spruce and birch, this was not the case. If something is interfering, we are done because we are off the main trunk, and for birch and spruce, this is something that cannot happen regularly. Now to the actual improvement. Instead of checking all x and z neighbors and the blocks up and down, we only need to check the current y position, as the main check block goes upwards from bottom to top. All checks for big or thick can be discarded, because the thick trees will use a different method as a whole. So how did I implement the determination for thick trees? First off, I copied the old determination, as it contains the general recursive method of going from bottom to top, which I think is a general thing that makes sense, right? You start somewhere and you end somewhere, and on the way you maybe check recursively for other logs or leaves that are not part of the trunk. We revert the null check because this time we need to exit the method if the bottom area is not set up properly. We can skip these data checks because they only make sense in the jungle tree determination. And we do not need to check all neighbors. We only want to check these three tree blocks at the current level, defined by the block face methods x and z, and the combination of both to get the diagonal block right. Finally, we continue upwards. Note that the deep argument leads to more thorough checks in the directions, but if we do not check deeply, we basically only add one more block outside the trunk, which will always be a leaf for spruce and birch. I added the new tree species implementation to the spruce tree type and ran a debug test. The result was pretty amazing. So when you do not spam check 27 blocks, but only the 8 that are required, you actually only need 83 block checks for a 42 block tree. Now the thick trees. The first attempt failed miserably. Only 1/4 got removed automatically. Who has spotted what I missed? Exactly. I forgot to actually call the method for more than north and west. Good job, me. So adding the other implementation should maybe fix it, right? Let's see. Right off the bat, the removal feels very fast, and leaves do not inhibit the removal speed as much anymore. Let's have a look at the debug. So after trimming down the check blocks, we went down to almost 400 check blocks for a tree that was 178 actual blocks, including leaves, right? This is pretty amazing because in theory we still have to check every height for leaves. Would I implement like a minimum leaf height? We could remove even more checks, but I feel like this is a big enough impact already. In summary, here are the numbers for the improvement of the spruce tree determination. These numbers represent the amount of blocks that are checked before the tree is destroyed, and it at least includes a material lookup, a list lookup, and possibly even more subtests in case it is a log or leaf. Before, thin trees did check 6 total blocks for result blocks. Afterwards, they did only check just under 2 total blocks for every result block, so down more than 66%. Thick trees did check almost 8 blocks for every result block, now they do check 2.2. That means a decrease of almost 75%. Up next, the second purely straight tree, the Birch Tree. I copied the whole implementation of the spruce tree and removed all references to the redwood tree type, replacing it with birch, and also removing all implications of a thick tree. So checks for bottom, the bottom determination method, and all things done because we support multiple trunks. After adding this new class to the list of supported types, I tested that the algorithm works for birch trees, which seems to be the case. Nice. Committing this and closing that case. Acacia. What an interesting tree type. I had some thoughts about how to improve the algorithm, both speed-wise and in general. One flaw I recognized quickly was that there was only one top recognized. That means I had a sub-method which went from the first trunk straight upwards, then tried to check diagonals and tried to get only one highest top block. In reality, those diagonal blocks can already start much lower, and there can be more than one of those, not only at the top, but in general. I think I've seen trees with 3 branches that all started lower than my former determination would have allowed, so I started implementing a new method, which used a clearer approach on the diagonal determination, which had 2 effects, but we'll see this later on. Instead of checking for the one top, I had a temporary variable called check and filled it with the current direction's highest top block, so I could later on compare it to eventual others and get the highest possible log for the tree determination. Instead of having each sub-method check for each direction like before, each branch can only go further in that direction, or up, so I only need to recursively check up and in the direction we were going already. This did cut down the check blocks by about a factor of 4. I removed the old diagonal check method and could remove a formerly supported thick tree implementation, as Acacia only has one trunk ever. I continued to finish the new implementation by replacing old general data with the new specific Acacia data. Furthermore, again, more removals because Acacia has no possibility to have a thick trunk. The next thing is quite unique to the Acacia tree, because of the fact that I have to practically follow the whole tree to each top anyways. I changed the way Acacia tree is calculated in the first place. Instead of having a calculate function that would then again have to travel through the whole tree to every possible top, I just used this first initial top discovery method getTop, which did travel through all the branches already. So I quickly added a new block list, and while looking for each top, I added the blocks I found on the way to this list. This way, after getting the top block, I instantly found and had all tree blocks on the way, and I did not have to recalculate this, which is how every other tree normally works. I added block-specific debug because I anticipated issues with this new diagonal algorithm, and I was right to expect this. Cutting down the first tree showed the flaw mentioned beforehand. Diagonal branches did not get caught because the algorithm first goes straight up and then tries to find branches. So before this only worked before the branch algorithm was so greedy to find attached or diagonal blocks in any direction ever. Look at all those diagonal blocks. Most of them were even at the top, so apparently my algorithm was not good enough. Alright, let's have a look at the code. It took me some time again, but I finally found my missing exclamation points. I basically only added the blocks if they already existed. Derp. So adding those where they belong should do the trick, right? The first works, yeah. The second, does not. What is going on here? Third, well, somehow also does not fully work. The next, perfect. The next, not so much. What is happening? Next. Also has remains, and again, so something is not going right here. I had a really hard time seeing my errors, so I had to browse through the whole of the new code. I found little things to optimize there, for example this top lookup. I can store this variable here and use it later on. Then I realized that I had set the top block in this method here, which always would run a risk of breaking the termination, because the top should always be the highest block available anytime. And so I created a local temp variable to store the current iteration in. To calculate the resulting highest top block, I should rather check all directions first and then get the highest block of each, right? So that is what I did. Each direction tries to get its highest diagonal block, and the result of this, or nothing at all, right, is put into the map. Afterwards, we iterate through the map to get the highest block, which will be the end result top block. Testing this again got mixed results, and this is why you get a sample as big as possible. The first two trees worked fine, but the third one did not, because I still did not see that I only checked for branches at the top of the initial vertical trunk. So here obviously again I skipped some time I invested into checking the debugs for what I did, and I finally noticed my error. I moved the checks for additions and for the top recognition to the top of the code, because the main trunk could contain the highest block in theory. I added a special catch for the first log, which is a special case because it will be skipped for the sapling replacement, and thus I skipped diagonal checking at this point. This is my final test, and this is how optimized acacia tree removal should look like. The jungle tree. I decided to base this off another branchless tree because that basically is what it is. Just change our references to the Birch implementation to jungle and we are done. Now to add the new thin jungle type and find the places where the actual instantiation works, because I need to check whether there are enough trunk blocks for a big jungle tree. If not, we assume it is a thin one. Here it is. So let's add all the neighbors and look for at least 3 more blocks. Testing it showed that I worked quite well. Committing this. Hooray! Up next, the big jungle tree. So this implementation is based off the old general tree determination, so we can remove the generics, replace them with jungle specifics. So I ran a debug to see the amount of blocks checked before optimization. Remember, this implementation is doing 27 blocks checking per block, and that for each trunk up and down it goes. To be specific, it was checking 4,000 blocks for a 240 block tree, including leaves. Alright, so let's copy over some things from the spruce tree determination, as it has an optimized way of getting all blocks for a straight tree. And let's remove unneeded things on the way. And I tried to fix some branches with this double check for blocks above the current blocks checked. Sadly, it didn't really work. Some clearly not attached branch stayed in the air. So I tried to fix it by checking further away from the trunk, but only in the deep checking method. So when we currently are on the trunk, the remaining logs were 1 block away from the trunk and thus not caught. This worked for all jungle trees until this one. Oh, and this one too. Not sure if I found it right away. I will be able to cut away a lot of footage on this one. What I am implementing here is a very complicated thing to explain in code, and it took me ages, so I will speed it up quite a ton. The issue was that a branch can go 2 ways next to the block face we are checking in a corner. It can either go farther in the block face direction or the other edge block face. Either and both of those will be caught by the algorithm I have. The only thing missing yet is the fact that, for example, the northwest trunk can have a west-facing branch that goes south, so switches to the southern trunk half. This kind of switching needs to be checked according to which trunk we are checking at the moment. What follows is a graphic that shows this in more detail. It will help understanding it. So I will skip this part now because what I did was basically plan and try out what you will see explained in the following. So this is a top-down view of what we are checking if we are processing the trunk. We will have 4 instances of this check. one for northwest, one for northeast, and so on. So for example, for the northwest trunk, we check for number 2, the northern branch, or the number 1, the west branch. The west branch could switch to the block here, next to number 8. The northern branch could switch to this block here, next to the number 3. And so it goes around. Every block face has to be checked for the neighbor with the main trunk, and that is what it did. Now it works very well. So let's move on to the dark oak tree. This will be a very short segment because given that the jungle tree is done, I could simply copy everything over from the jungle tree determination and remove all parts that deal with branches. So running a debug, I learned that for a tree that has 94 blocks, the algorithm formally looked over 3000 blocks. This can be reduced big time, again, because I only do need check for branches in the trunk edge directions. This is what the new jungle determination does, and thus it was very easy to work in for this tree type too. The only thing that the dark oak has for it is a range check that minimizes the area it checks to 2 blocks away from the trunk, as dark oak trees can be very close to each other. Furthermore, the highest trees can be even higher than the highest trunk block we found. So I changed it to support 2 blocks higher than that, which is what I found was the max that could happen. So this is the result. For an 80 block tree, it only does check 133 blocks now. This is an improvement by a factor of over 20. Nice. Now the mushrooms. This is a very straightforward thing, as I basically hard-coded the shapes of the mushrooms. So I split the mushroom determination, which did support both shrooms, with hack fixes for the red, into 2 basically separate things, which can be hard-coded. Furthermore, I found out that while testing that there are huge mushrooms of over 12 blocks high, so I added support for those. The layout is the same though. First off, the brown mushroom simply goes straight up, from bottom to top, just like every other tree type. But when it reaches the top block, it continues outwards, calls a separate method that continues outwards, right? This method is called with the general 4 main directions, and in 2 cases it will just continue in those directions until the edge, and the outer 2 directions will branch off to the former directions. So we go from the middle to out to all directions, and north and south will branch out to east and west. Again, so we can catch all blocks of the top part. That was it. I hope we learned something. I definitely did.